So there are different approaches to statistical mechanics. The approach that we will be discussing today is known as the microcanonical ensemble. So, but before I tell you what the microcanonical ensemble is, let me first state what is the fundamental postulate of statistical mechanics. So what is the fundamental postulate? It turns out statistical mechanics is about democracy. It is a very democratic field, and the fundamental postulate reflects that. And it says that for an isolated system, in equilibrium, all accessible microstates are equally probable. Okay, so this is the fundamental statement of statistical mechanics. Now let's unpack the statement. So let's ask ourselves, what does it mean for a system to be in equilibrium? Because we have to restart it, right? Because we cannot use our idea of equilibrium that we used in thermodynamics, because then it'll be cheating, right? And we have to understand what microstates are. And we have to say, what do we mean by accessible? I'm assuming that we all know what probable, equally probable means, right? Equal probability. And we all understand what isolated system is. Okay, so let's dive into these technical terms. So what is equilibrium? So suppose we have some system which is isolated. So we isolate the system from its environment. Then we expect the system to reach some sort of steady state, right? We reach a system reaches some kind of steady state. A steady state, after a long time, after it's after it is isolated, right? So what happens in the steady state? What happens is that the macroscopic parameters don't change with time, right? So when the steady state is realized, the macroscopic parameters describing the system don't change with time. But that doesn't mean that the microscopic constituents do not move, right? So it doesn't mean that the microscopic constituents are stationary, right? So if you look at a gas, we So we bring two gases together, you know, suddenly they start mixing, they start exchanging heat, you know, blah, blah. They reach the, you know, but after a while, you know, the macroscopic, you know, quantities describing them reach some steady limit. But if we have a microscope and we look into the gas, we see that the gas molecules are still moving around, right? So this is what we mean by equilibrium. So I know that not all of you have had quantum mechanics, but I'm going to give another example of equilibrium from quantum mechanics. How many of you have had some quantum mechanics?
I had quantum mechanics.
I haven't had any formal quantum mechanics, but I watched some on the internet.
Okay.
I had some from the MIT playlist. That's it.
Okay. So, you know, this is not like, even if you don't understand what I'm saying here, it's fine. When we actually do some calculations with quantum mechanics, I'm going to make sure that I give you the necessary background. But here, I just want to motivate the idea of equilibrium from a more quantum mechanical point of view. So what happens is that in quantum mechanics, you know, you have a system. So you have a quantum mechanical system. It can have some allowed energies, okay? If the system is isolated, then the number of energy levels allowed are discrete, okay? It can be infinite, and we will be dealing with, or a very large, but it's discrete. But the discretization doesn't have to be, you know, sometimes you can even have continuous, like almost continuous. That's not important. So these are the possible energies of the, you know, of the system. And what happens is that there is a matrix or a linear differential operator called the Hamiltonian. So Hamiltonian is either a matrix or an operator, and these EIs, these energies are eigenvalues of this matrix. So it means that there are some vectors called psi n, which are eigenvectors of the Hamiltonian, right? So this is the eigenvalue equation. Are you all familiar with the eigenvalue equation?
Yes, sir.
Yes, sir.
Yes, sir.
Anyone who is not familiar with the eigenvalue equation?
Sir, I'm not very much familiar with it.
Okay, so the eigenvalue equation is, the simplest way of describing it is that suppose you have a matrix, a square matrix, okay? Now, so the square matrix is, suppose we take it to be a 3x3 matrix, right? So I'm not writing down any specific matrix. So a 3x3 matrix will naturally act on a three-dimensional column vector, right? Now, if that column vector is such that the action of this matrix acting on it gives you the same column vector up to some number, lambda, then this equation is called an eigenvalue equation, okay? And it's an eigenvalue equation. Eigenvalue means characteristic value. And this is the eigenvalue. Okay. So this is a characteristic value or an eigenvalue of this matrix. So what does this mean? This means that this matrix is somehow characterized by these numbers. Okay, so, and you know that if you take a matrix you can do a similarity transformation on the matrix and get a new matrix. Now, the nice thing about eigenvalues is that under a similarity transformation, the eigenvalue doesn't change. So that if the eigenvalue of H is, say, lambda 1, lambda 2, lambda 3, this is the set of eigenvalues of H prime will have the same eigenvalues, okay? So what I'll do is that I will make a tutorial on eigenvalues so that you can, those of you who haven't done eigenvalues, you can learn about it. Those of you who know about eigenvalues can apply them to a cool physics problem, okay? So, so idea is that the energies are the eigenvalues of the Hamilton operator, of the Hamiltonian operator, okay? Now, if the system has some, observable O, meaning that O is another operator or a matrix, then we can work out what the average value of O is. The average value of O is going to be the most likely value. Then that is given by the probability that our system is in the energy state N. So here, N is labeling the energy times the expectation value of this operator. It's an inner product, okay? So, so this is basically the average of some observable. Now, what are PNs? PN is the probability that our system has energy E of n. And this has nothing to do with quantum mechanical probability. This is classical probability, okay? So now the thing is that if our system, if this probability distribution is independent of time, then we say that our system is in equilibrium, okay? So if I bring two systems together and then, I look at what P is, this probability distribution, because these two systems have just come in contact with each other, they will be exchanging energies and stuff like that. This will not be independent of time in that case. The energy levels will be shifting, until they settle down. It'll dissipate some energy, or it'll reorganize itself. At some point, it'll settle down to the energy will be distributed through all its component, and at some point it'll settle down in some steady state, so that the system which had a time dependence will eventually become a probability a probability distribution which doesn't depend on time. And it's only when this happens we say that our system is in equilibrium, okay? So this is another example, a quantum mechanical example of what an equilibrium means. Okay, so it's okay if you don't understand this, okay? So don't worry too much about it. But here you see that psi n, which was a solution to the eigenvalue equation, this is for a given value of energy, En, psi n is telling me what the configuration of that system is. Now, typically for a given value of energy, there'll be many, many configurations, microscopic configurations, that will give rise to the same energy. Okay? So all these microscopic configuration with the same energy, psi n, so this is a set. These sets are what I'm calling microstates. So classically, let me do a classical analogy. Classically, suppose that we have n gas molecules, and these gas molecules have some average kinetic energy. So for given kinetic energy, a total kinetic energy, for a total kinetic energy, there could be many different configurations, right? In fact, if the walls are perfectly elastic, this configuration is always changing. So all these different possible configurations which give rise to the same total kinetic energy, all these different configurations are what I'm calling microstates. Okay, so now that we have defined what microstates are, we have defined what an equilibrium is, we can now define what accessibility is. So what we're going to say is that we are going to fix the energy E. We are going to fix the total energy E. And then what we are going to say is that accessible states are all those states with energy E's. Okay? So accessible states are all the states or microstates with that energy E. So now that we have defined all our terms according to the fundamental principle of statistical mechanics, the probability of the energy En is going to be 1 over omega E. Okay, so let me just recap. Remember that for an isolated system in equilibrium, all accessible states are equally probable, and that probability is given by this thing, right? Because we're dividing by all the number of microstates, that is the statement of equal probability, right? Each of these state has the probability of 1 over the number of total microstates in that energy. Okay? So this is what is, so we are also assuming that, if the energy is fixed E is energy, the probability, or En, let's call it, the probability of En prime, where n is not equals to n prime, is 0. Okay? As this follows. And this proposal is called the microcanonical ensemble, or ensemble. Okay? Okay, any questions?
So does the microcanonical ensemble state that if there are omega of E microstates, all those are equally probable?
Yeah.
Omega E, is that the energy of
Yeah,
the microstates?
Yeah, sorry, I should have made that clear. Yeah. Omega E is the number of microstates with energy E. Yeah, thank you very much. That's a very good, I skipped over that.
And what is the relationship of N and the energy of those N states?
Yeah, so E is the energy, N is the nth energy level. So this is just, because the smallest energy level is E0, then we have E1, E2. So N is an integer that just labels the energy, which energy state you have. So when we are saying P of N, it's just we are just being, it's a shortcut for the energy or the
So
energy level. Okay?
n here are the discrete probable energy of the microstates, and probability of n is not the probability of particles. Like n here is energy, right?
N here labels the energy. You're right.
Oh,
Exactly.
acha.
Yeah.
Thank you. And last question from me is, what is the meaning of P of n prime is equal to 0? I didn't get that.
Oh, yeah. What I'm saying is that we are fixed the energy to be En. So if the energy, so the probability of a microstate whose energy is not En is 0.
So the n is not equal to n prime. Would that be the correct form?
Or N prime is not equals to N. Yeah.
So not equal sign.
You're right.
Oh, that was the confusion. Thank you.
Yeah. Thank you very much. Yeah. Sorry, I didn't. Yeah. Very good. Thank you. Okay.
Yes, sir.
Okay. Shall I carry on?
Yes, sir.
All right. So these numbers, the number of possible configurations, are crazy huge. So, for example, we took our n to be, say, 10 to the power 23. Now, suppose these 10 to the power 23 are spin half particles, say electrons. Then if you just consider the spin configuration of the electron, an electron can have spin up or down, right? So each electron can have 2 configuration. So if we just look at, I mean, there'll be other degrees of freedom, such as, its motion. But if we ignore all of that, if we just look at what the spin degrees of freedom give us, the number of different types of configuration, we see that this is going to be 2 to the power 10 to the power 23, right? So this is a huge, huge number. Okay, so these are numbers that, so it's clear that we are not going to be able to do any kind of, applications of detailed physics to this number of states. So, so that's why we need statistics